today I'm going to talk about 6G architecture, which is as a cellular network 2.0. So it might be a bit radical compared to the vision we have seen previously from all the presentations. But I believe there is a need why we need such a radical vision in 6G. This vision, you can see it as a networked computing perspective vision. And then I believe this can give you some insight related to making some consensus in designing the 6G architecture. This is kind of an ordinary perspective of 6G. I'm just citing the Huawei's the figures, but I'm not only talking about the Huawei's vision. So the 6G is seen as a kind of improvement from 5G, but is it going to be sufficient? That's the question. So unfortunately, in my point of view, the cellular network business is dying like a frog in a boiling pot. Maybe you don't agree with this, but if you are in the university, like myself in SNU, you cannot expect the best student in EE or the CS coming to the communication field, right? I believe you already know about that. Why is it like that? So the communication business is considered to be saturated in some sense. Like we already know the revenue is saturated and the operating income is saturated in the global telecom operators. Compared to this, the AWS, the Amazon Web Service, is growing linearly as time goes by, and their operating income is also growing really fast. And we already saw the power of the generative AI like ChatGPT, and after seeing that, I've seen lots of professors saying, I'm feeling really frustrated because the ChatGPT's innovation is too far to follow, right? So in our field of communication, we are kind of losing the real innovations that can translate to the business, the benefits that we can provide to the users. So why is it like that? So currently, we are talking about AI native architecture of 6G, which is integrating all kinds of machine learning, the mechanisms into the communication system. And we were talking about improving the bandwidth, throughput with LIS or other types of like MIMO technologies. We have been pretty good at doing that, like improving the bandwidth and reducing the signal level latency. But the problem is those benefits are not translating to the user benefit. And there is a reason, and I believe if your background is like a communication or the physical layer, it would be hard to accept this. But in terms of like a programmer's point of view or the application's point of view, this throughput improvement would never be perceivable in the application's perspective. And I will talk about that in this the talk. So we probably need to look into the problem in the architecture. So you can see from these figures that there is a good architecture which is visually looking good, I mean, aesthetically looking good, and which is also very efficient in terms of this construction. And we have been using this internet with this the hourglass architecture, and it has been there for more than 70 years, and it is pretty successful so far. And we had a very nice vision of this wireless communication with the cellular network design, and it was working so far so good. But as I mentioned, even though we improved the throughput, it's not translating to user perceivable performance anymore. There must be a reason, right? And there are companies like Apple who are really focusing on the design of this application level performance and design their computer architecture and the network architecture, software architecture based on this like user perceivable performance. I think we need to learn from this practice. Okay. And how can we emphasize the importance of this radio technology? Actually, that's the most important question to be answered. what is the reason to pay more for using the radio bandwidth or the radio resource, right? If we just watch YouTube videos, which is like a large volume, how can we justify that providing more bandwidth is related to paying more of the money from the users or other businesses? Unfortunately, the throughput itself is not going to work for claiming more of the payment. However, we have to see a very nice example from cloud computing. In the cloud computing case, they are actually charging more money when users want more GPUs, right? More CPUs. If users claim more of the computing resources, actually the cost is linearly increasing. But in this wireless communication, there was no such pricing model, and it is not likely to be accepted by the users. So how can we translate this radio bandwidth into this economic or the financial benefit? That's a question, and I have been struggling to find the clue. And because one of my research background is mobile computing, I was lucky to find out this graph. Actually, this graph here, in the center upper corner, that was the graph shown in the paper of computer architecture paper published in the Communications of ACM 2019, published by John Hennessy, who was the former the president of Stanford, and he is currently the chair of the Alphabet company. And he mentioned about the golden era of computer architecture based on this graph. And we are so lucky to have this property at the time of 2023, where we are designing the 6G. And this graph is talking about Dennard scaling. I guess some of you have ever heard the Dennard scaling, and some of you may have not heard of it. So it's related to the efficiency of semiconductor chipset manufactured for the limited platform. So all we know is the Moore's law is still working. I mean, the 2 times of transistor density every 2 years, that is still alive. However, the problem is the Dennard scaling, which was actually too good to be true. That is, within the same size of the semiconductor, even with the densification of the transistors, the power consumption would stay the same. Because as you go for the finer process of semiconductor the manufacturing, then the current that you need to make these transistors communicate would reduce. And if you combine all these equations, then you will come to an end that the power consumption per unit size of the transistor is staying the same. However, because of the leakage current problem, as this a process goes to the smaller than a 2 nanometer process, the power consumption suddenly became soaring up. As you can see, from 2012, the power consumption per unit size of the semiconductor is not at all staying the same. Because of that, if you have ever bought a graphic card for yourself or your children, the graphic card size of NVIDIA is becoming like a monster these days. So because of the heat dissipation handling with that large size of the cooler, then makes the size of the GPU larger and larger. But if you translate this problem into this mobile business, think about the form factor of this cell phone, right? Or the form factor of those wearable devices. It's even smaller than this smartphone, right? So inside this form factor, you cannot install any of the heatsink or any of the cooler which can support the power consumption of powerful or the advanced semiconductor chipset. Meaning that the performance of this mobile device would have larger and larger gap compared to the computing which is provided with supercomputing or the cloud computing at the moment. So Samsung already pointed out that in their a white paper published in 2020, as you can see, the mobile GPU capability is improving. However, the demand from the user would increase even faster than that. So when I first saw this graph, I thought this is from pure guess, but it's not like that. It's actually from this like a semiconductor, the background knowledge, and this is not just the regression-based graph. This is the practical prediction that you will actually see from the semiconductor business. So the mobile system, the cellular network system now has a very strong weapon. That is, the mobile device's computing power would not grow as fast as what users need. So if we can design the cellular network to make this mobile platform work over the network, meaning that implementing connected computing or the networked computing or exo computing, whatever you call, if we can implement that, which is not distinguishable from local computing, then we can claim the role of this wireless communication, role of the cellular networking is really precious compared to previous just dumb bit pipe that we provided to the users. So this video, I guess you have watched this many times from Microsoft HoloLens demonstration. You see the huge volume of the data is transmitted over the distance through, of course, cellular network. And the interaction in this video is nearly in real time. So the real-time interaction provided over cellular network, actually that's invaluable. And if we can achieve this, of course we can claim, more revenue. We can justify more revenue. And we can fight with the network neutrality or the strategical decisions made by the politicians. I believe we can provide some justification if we can really achieve this kind of platform. And some of the companies, like computing-based companies, are already aware of this, and they are building their visions to enable this with their high-performance computing infrastructure combined with some of the open softwareized radio access network. So the companies like Meta or the Microsoft are investing quite a lot to standardize this RAN through ORAN or other types of the community so that they can control this radio access network to provide this the indistinguishable computing performance to the mobile platforms that doesn't have the good enough capacity of handling power consumption. And this is what we have envisioned from like a 4G and the 5G. So providing like ChatGPT like secretary service over the network in real time. And based on this, we may be able to justify the cost of this wireless resource. So some companies which were successful already in standardizing their data center architecture with the concept of decentralized or the disaggregated computing, they are also trying to standardize this radio access network. And the reason why they are interested in this, some people may say that is to lower the cost of these devices. That is true by adopting like a multi-vendor solutions. But I believe the more important part of doing this is to revolutionize the cellular network so that we can actually provide indistinguishable computing performance to the mobile devices which are not going to be sustainable in providing user satisfactory services. Okay, so now I should tell why providing more bandwidth, why providing the more of the spectral efficiency, why renovating energy efficiency, that's not so important in enabling the vision of this 6G. So as we all know, we have done lots of things in the physical layer, but I was saying that translating these innovations to user level performance is pretty difficult. The reason is as I'm going to show you in the next slide. And one part that I have to tell you is the 6G is going to be placed in the location where the throughput and the latency is beyond the residential internet. So there will be 0 services that 6G can enjoy, meaning that for those the services that we are really interested in providing to the users, 6G developers should be also providing solutions to develop such new kind of services. There is no help from the internet because the internet is not reaching that level of the performance. Right? Okay, so the Apple, when they provide a solution like this Face ID, they actually release this hardware in package with the software. They provided the API to the developers, and this developer who is not aware of anything in this like hardware details, they were able to develop pretty good services. Meaning that in 6G, when we try to bring this like a top level service developers to our the cellular network business, then we need to provide some kind of API, for example, like a cellular API or the 6G API to those developers so that they can just devote themselves to prepare the services itself without considering too much about the problems of the network. The problems that we all know, that's like a fluctuating performance when we move and if the distance is far from the cell tower, we naturally accept that the performance is degrading. But if we accept that, then how can some developers provide reliable services to the users? So there is something wrong or the strange in the philosophy of the cellular network that we really have to change. So if we can provide this cellular network API, which is providing complete solution for these application developers, then we can revive this cycle of the technical innovation brings new profit and new revenue, and it is invested to the infrastructure. We can revive this good cycle. Okay? So how can we actually implement this in the 6G? And there must be an architecture, and I believe this is a very a nice architecture to think about together to make some consensus in 6G design. So when user device, whatever the device is capturing some data, just like the automated vehicle, when they sense the data, they probably need to send the data over the network. And this network, inside the network, there must be some computing, which is to provide actual services to the user. Most of the cases in the next generation system, we believe AI-based analytics is going to be a killer service. Then the results should be returned to the user, but this timing from the uplink to the downlink of the result, that should be bound within some specific time so that the user never feel the difference between this local computing and the network-based computing. Right? How can we do this? Can we do this with the 5G architecture, 5G advanced architecture, or the 6G architecture that we have discussed in the earlier sessions? Can we do this? I believe not. Why? So when you see this problem in this figure, very, very simple figure, when the application, whatever the application, is sending out a data of X megabyte, then it should be delivered to this computing system within some bounded time. Or, of course, if I extend this to the round trip, then the uplink and the computation and the downlink, it should be bound to B time. For example, 10 millisecond or 20 millisecond, whatever the millisecond that the service requires. Then the current system is experiencing some serious problem in controlling data rate of all, right? D is the baseline delay, so URLLC somehow covered to reduce this baseline delay to like a 1 millisecond, that's good, but the real completion of this data delivery is done when X is fully delivered. So D plus X divided by R, that's the equation, and unfortunately this R is controlled by the situation. So we cannot manage this equation to be bound within some b. So what should I do then? Of course, some people may say, yeah, dynamic RAN slicing would be the solution. But dynamic RAN slicing, what does it do? It is actually reserving this radio resources from the beginning to the end without knowing when this application data would come out. So we have to sacrifice lots of radio resources, and most of them would be wasted. And it is not even possible to properly allocate these radio resources in advance, so lots of waste would be expected. So I believe we need to change our mind in designing the architecture of the cell network. That is, originally, what we do is like bottom-up approach. Based on this Shannon capacity equation, we just accept this situation. When the user is far from the cell tower, the channel would be bad. If the channel is bad, even though I maximize the efficiency of this radio, I may not be able to provide good throughput to the user. And once I get the throughput, then the application doesn't have any control of improving or reducing that bandwidth. So this is completely bottom-up approach. But as I mentioned, with this bottom-up approach, it will be very, very difficult for applications to run smoothly over cell network. So if we change this vision from bottom-up to top-down, then we can do something better. When application needs to send, for example, X megabyte, then maybe the cell tower can know that information in advance and allocate the radio resources on time so that this data can be delivered to the computing resource on time or in time. Of course, some people may say it will degrade the performance of spectral efficiency. I know, but if we don't sacrifice spectral efficiency in trade-off with this application performance, I believe there is no hope for the current architecture. So we kind of published the communication magazine paper, which is explaining this architectural change, and I believe this paper is explaining what is required to properly allocate radio resources to make this application performing smoothly over the cell network. Okay, fortunately, this type of a reverse design, like a top-down design, can be actually implemented in the ORAN architecture. I believe there is a group of people who are specialized in computing and application design. That's why this ORAN architecture is kind of reasonably designed. So as you can see here, there is a near real-time rig, which is connected to DU and through the open frontal to RU. And it is also connected to the cloud computing resource. So there is an option in this ORAN architecture where you can directly control the time budget of computing and time budget of radio transmission. And there is an option that you can intentionally control this radio resource allocation from the application understanding. So I guess due to time, I have to jump to the final slide. So the application data unit's completion time guarantee, that's more important than anything in the next generation architecture, because we don't need to think about individual application. If we can do this, any kind of application which needs the real-time interactions, they can be implemented, realized. Of course, this is all coming from the differentiated pricing model, which is to price the radio resources more valuable sometimes than the computing resources, and less valuable than computing resources time to time, depending on the resource need of this radio part and the computing part. So we'll skip some of the detailed explanation. And the last one. Yeah, maybe we can have some roadmap to achieve this performance guarantee of application level. just like what people have done in the automated driving from level 0 to 5, we can define the performance guarantee level from 0 to 5. And I believe current 5G is in the stage of level 0 in terms of performance guarantee for application. So what I can envision, or what we can envision for the next generation solar business is the combined business of computing and the networking. And in this type of business, when this time for the application service is given, for example, 30 milliseconds, then how to split this 30 milliseconds into networking part and the computing part would be a very interesting question. And if there is a company, for example, Meta, who is running their cloud computing platform infrastructure as well as some radio access network, then they will think about something like this. What is the radio resource cost calculated in terms of GPU cost? Which one is more valuable? If we can make this happen, then I believe we are very successful in reviving the cellular network to be a future-proof form of next generation network. Thank you.